Hi everyone, welcome to the exercise class. So today the plan is following. I'm going to discuss the content of two exercises in this week's exercise sheet. The first exercise concerns the Lindbladian evolution, and the second concerns, and we will walk through the whole derivation of how we get the master equation with the Lindbladians. And then the second, we'll look at how we can generate some entanglement with a thermal machine. Okay, so let us start. So to start with Lindbladian evolution, so first thing we will look at, we'll start from very easy consideration, and we'll just look at the Schrödinger equation for mixed states. So usually we write the Schrödinger equation only for pure states, but we can also generalize it for like any state. Okay, so let us assume that the system is undergoing evolution described by unitary U. Then suppose that we want to write out the state of the system rho at the time t plus delta t. Well, delta t is the small change. Then it can be written as u of delta t, rho of t, u dagger delta t. So we just take the state of the system at time t and then evolve it for the small time delta t. Okay, let us just write this in terms of the Hamiltonian. So this would be e to the power of minus I over h bar delta th rho of t e to the power I over h delta th. Now let us use the Taylor series expansion for the exponential. And so what we get here is identity minus I over h delta th rho of t 1 plus I over h delta th plus some terms that we leave out of the order delta t squared. We're not interested in them. Okay, so if we open up these expression, what we get is just rho of t minus I over h delta t h rho minus rho h plus again this leftover terms. And then we can rewrite this expression the following way. So we get that rho of t plus delta t minus rho of t. Then we divide this by delta t, and we assume that delta t goes to 0, as to 0. Then this is equal to minus I over h, commutator of h and rho. So this is, we're just taking the limit of this expression for the very small amount of time, delta t. Okay, and the expression on the left-hand side is exactly the derivative of rho with respect to the time t. And so hence we get our equation d rho or dt is equal minus I over h bar h rho. So this is essentially, you probably have already seen this equation. And this equation essentially tells us how the state rho evolves of a system if we know the Hamiltonian which governs the system. Okay, so this was kind of easy. So the next concept that we will need is the concept of open systems. So what we just looked at was kind of the evolution of a closed system, because we knew kind of the unitary which was governing the evolution of the system, of the whole system. And so it's, for us, it was easy to write like at an arbitrary point in time what is the state of the system is. However, this is not always the case, and sometimes we need to consider systems which can interact with the environment, but then for some reason, for example, the Hamiltonian for the joint system of the target system and the environment is too big, or for some reason we don't know exactly how it looks like, or we don't, or usually the environment is much bigger than the target system, and we don't want like to get mingled with calculating that. So that's when we kind of say, okay, our target system is an open system. We know that it kind of interacts with the environment, but we just disregard that, and we in the end trace out the environment. But of course, in this case, the equation that we just derived will not work, because we're like, the evolution of this open system, as in the target system alone, is not unitary. Okay, so to recap this, so open systems, they are based on a concept that system can interact with environment. And how do we formalize this? Well, we just say that we know that the global Hilbert space is the joint space of the system S and the environment E. And usually we also assume that the system is much smaller than the environment. Okay, and also the Hamiltonian of the, which describes the interaction between the system S and the environment E, is also, can be quite large, or we don't know it. Then we are interested in the evolution of the system S alone, and usually we just write this out as, okay, we evolve the joint system under the unitary USE. And then we trace out the environment. But again, because yeah, let me make this a bit bigger. Yeah, because of this reason, or because we don't want to like write out this huge unitary, it's easier to just describe this evolution of this target system as TP-CPM. So TP-CPM, just to remind you, is trace preserving completely positive map. Another assumption that we make when we write this, adding to our motivation also that the environment is much bigger than the system itself. So we assume that the dynamics of the environment are much faster than the interaction that happens between the system and the environment. So in a sense, this allows us to neglect the previous correlations between the between the system and the environment when we just considering this TP-CPM describing evolution. So I'll explain it in a moment. So the dynamics on the environment is much faster than the interaction with the system. So a good example of this would be like, think about the cup of coffee, and then you can think that, okay, so the molecules of coffee are somehow interacting with the air, but because we're looking at we're looking at the interaction between liquid and gas, like intuitively you can already see that we can assume that these molecules of coffee always interact with the new molecules of gas, because so they don't kind of interact with the same all the time, but they always interact with a different set of molecules of gas, because the dynamics of gas and the kind of distribution of these molecules is much faster than the time that the coffee molecules take to interact with this air molecules. So here it's the same intuition essentially. Okay, so, but the main take-home message from this open systems is that we describe their evolution with this TP-CPM map. Okay, and now we come to the Lindblad equation, which is our goal. So Lindblad equation is essentially just an extension of Schrödinger equation, but for the open systems. So our goal is to write something like the equation we considered in the first part, like this d rho by dt equaling minus I over h bar commutator of rho and h, but taking into account that we're looking at the dynamics of an open system. So there are going to be also some terms, like some terms which add to the fact that the evolution on the target system itself is not unitary. So intuitively, we must expect something like this equation above, but with some added terms. Okay. So let us proceed in the same way as we did in the first part. So we will just consider the state of the system at the time t plus some small time delta t. So rho of t plus delta t. What is it? This is just our map, TP-CPM map, epsilon, applied for the time delta t at the initial state rho of t. And we also assume that we can write it as rho of t plus some small addition delta rho, where delta rho is much smaller than rho. And this of course follows from the fact that delta t that we're looking at is much smaller than t. Sorry, not t, but like, yeah, than 1 with the appropriate units. Okay, so now what we can do, we can use the fact that we know from quantum information theory and just decompose our TP-CPM map as a Krauss decomposition using the Krauss operators. So let me start maybe on the next page. So basically we can just rewrite the action of this map as sum over k from k0 to infinity, ak rho ak dagger, where this is a Krauss decomposition. Now let us rewrite the Krauss operators in the following way. So the zeroth operator, or whatever we label as a zeroth operator, we rewrite it as identity plus delta t L0 minus ik, where L0 and k are some bounded operators that we choose. They're also Hermitian. And then AK, we just decompose it as, or rewrite it, let's say, rewrite it as LK square root of delta T. So all of this operators are bounded, and these are additionally Hermitian. So this is like we just adjust and choose these operators, which, as you probably see from the name, will become Lindbladian operators. And K, we will come to that later. But we just adjust them such that A0 would be equal to this, and AKs are just scaled with the respect to LKs. So OK is just bounded. Okay, now let us see what merit we get from rewriting Krauss operators in this way. So the 0th element in our expression of the map will be this 1 plus delta T of 0 minus IK rho 1 plus delta T of 0 plus IK. Here again, as in a previous consideration, we are only interested in the terms which are of the first order and delta T. So everything that is of the second order and higher, we just throw away. So here we get rho plus delta T L0 minus IK rho plus delta T L0 plus IK rho. Sorry, I messed up the order. Will be rho L0 plus IK. And this we plus, also write it O of delta T squared. And this I can conveniently rewrite as rho plus delta T anti-commutator of L0 and rho plus I delta T commutator of rho K plus O of delta T squared. So anti-commutator is just L0 rho plus rho L0. Okay, so this was the 0th term. Now all the other terms are pretty straightforward. They are just delta T, LK, rho, LK dagger. Okay, and now let us come to the complete expression. So this will be rho of T plus delta T equal sum. It's just Krauss decomposition. Now we just plug in our expressions. So we get rho of T plus delta T L0 rho plus I delta T rho K plus delta T LK rho LK dagger plus our leftover terms of the delta T squared order and higher. Okay, so now we do the same trick. We look at the following expression, rho of T plus delta T minus rho of T over delta T. Delta T we take tending to 0. And what we get here is the following. So we get L0 rho minus I commutator K rho. I just switch the order of the terms in the commutator because it will be easier to see the analogy in a moment with the previous equation. And plus the leftover stuff. Oh yeah, because I am not very observant, I still need to add here the sum. Okay, and here we have our sum, LK rho, LK dagger. Okay, so let me rewrite this on the next page because the first, the term on the left-hand side, this one, as delta t tends to 0, it is again the derivative of rho with respect to t. So it will be d rho by dt equals L0 rho minus I k rho plus some from k equal 1 to infinity lk rho lk dagger. And now, since we still have some kind of some sense of freedom in choosing what our operator k is, so from here, we actually already see what we have to choose as the operator k, which would be a physically meaningful choice, because as we remember, for the unitary evolution, we would have kind of that's d rho by dt equals 1 minus 1 over h bar Hamiltonian h rho. So from this, it follows that we should choose k as hs over h bar. In that case, the case when all Lindbladian operators L0 from L0 to LK are zeros, we just come back to our usual Schrödinger equation for the mixed states. Okay, so with that in mind, we write our final. Let me maybe exchange this. We write our final equation plus 0 plus sum of these. So this is called a Lindblad equation or master equation. And it is just an extension, as I already mentioned, it's just the extension of the Schrödinger equation for the case of the open systems, where we kind of in the background know that the system is interacting with the environment, but we don't want to include the environment explicitly in our consideration. So this was basically one half of the exercise. And then one small part that is left, actually, one can also simplify this expression further. So one can find how the operator L0 is connected to all the other operators LKs. And this can be done using the property of the density matrix, that the trace of the density matrix is always 1. So because the trace of the density matrix is always 1, it means that the derivative of the trace of rho would be 0. So using the fact that d by dt of trace rho equals 0, so yeah, so just add trace everywhere. One can find how L0 is connected to all other operators LKs. So it turns out that L0 equals minus 1 half sum LK dagger LK. And because of this, we can get rid of the L0 and just rewrite this as the following. Okay. And now we only need this Lindbladians from ranging from 1 to infinity, or from 1 to depending on how many Krauss operators you have in a Krauss decomposition. Okay, to make this a bit more clear, I'll give a simple example of such a process happening. So we'll be looking at the qubit, and we'll be looking at the process which ensures that the qubit is always converges to the ground state. And we want to describe this process as in we want to find the corresponding Lindbladian operators, LKs. So yeah, let us consider an example. So we have a qubit, and the process is such that it always takes the state to the ground state in the limit of the process running infinitely. And this happens for every state. So in this example, we actually need only one operator, L1, and of course L0, but it is already defined by L1. So, and the operator that we need is lambda 0, 1. We also assume that the Hamiltonian of the system is 0. So let's say that it doesn't have an energy gap between the states. Okay, then let us kind of show that this evolution is described by this Lindbladian. So let me maybe copy this from here. So copy, paste. Okay, so what we need to do is the following. So this kind of goes away because HS is 0. Then L1 dagger L1, or can already write this minus 1/2. This is L0. Okay. And now we just need to write down our equation and indeed see that it takes any state to a ground state. So here I'm writing the anticommutator of L0 with rho. And here I write the rest, so namely one Lindbladian L1 acting on rho. Okay, suppose that rho has the following entries. Then the anticommutator of 1, 1 and rho is, so will be this plus this, which will give us 0, B, C, 2D. And the other term will just give us the 1, 1 term, but in the entry for 0, 0. Okay, so then d rho by dt is minus lambda squared over 2, 0 b c 2d plus lambda squared d0000. Okay, and this is the same as saying, oh, since we're taking the derivative with respect to t, this is dA by dt, dB by dt, dC by dt, dd by dt. And then we can solve each of these four differential equations separately. But here we already see that, for example, we have the form as dB by dt equals minus lambda squared over 2b. So obviously the solution to this is the exponential, so the decaying exponential. And the same goes for for C and D. For A we can actually just infer from our solution for D, because we know that the trace of the matrix has to always be equal to 1. Okay, and then the solution would actually be rho of t 1 minus d e to the power minus lambda squared t, b e to the power minus lambda squared t over 2, c e to the power minus lambda squared t over 2, and here we just have d e to the power minus lambda squared t. And we see that in the limit of t going to infinity, all of these terms will die out except for the term corresponding to the ground state. So this tends to 1, 0, 0, 0 as t goes to infinity, which is the ground state. Okay, so this was an example for the Lindbladian, describing a process for a qubit, the process of decay to the ground state. As you've seen in the lecture, these equations can also be used to describe actually any interaction with the environment, including the thermalization. Okay, so this was all for the Lindbladians that I wanted to say. Now to the second exercise, which connects to this master equation things a bit, but you will not have to solve it directly there. So the second exercise is about generating entanglement, or whether we can generate entanglement or not with a thermal machine. And we will look at the following setting. So suppose that we have two qubits, and they're similar. So they're identical, actually. These are just two qubits with the ground state and excited state, with the energy gap E. But one of them will say that it's cold and label it as C, because we assume that it is connected to the cold bath, and the other one is hot, as in it's connected to the hot bath. And we'll label them as C and H. And there is interaction happening between these two qubits, which is energy preserving. So this interaction, yeah, you probably already seen it before, as in so if there is some population here, it goes down, then the population in the hot qubit goes up, and the other way around as well. So this is kind of equal energetic exchange. And though we say that they're coupled to these baths, we actually make the mechanism, in this case, we make the mechanism of the coupling explicit. So we don't just say, oh, they end up in a thermal state. Here we actually write down our evolution more explicitly. So suppose that we suppose that this coupling to the baths, it happens through rare events at each time step. So essentially, like at each time step, at any time, each qubit is reset to its thermal state with some small probability, but it can also, with some probability, it can also be left unchanged. So we're looking at this process. So it's like, yes, it's coupled to the bath, but and with some probability, it can end up in a thermal state, but with some probability, it will just stay as it is. Also, kind of also keeping intact the correlation between the qubits. And then the idea is that we will now write down the equation for this process, and then we will analyze the steady state. We need to analyze the steady state of this equation and see if the steady state is indeed entangled between these two qubits, and if entangled, then how big essentially is entanglement. Okay, so the equation, the master equation, which describes this process of going into the thermal state with a certain probability, can be written as, so first, as we already seen, we have this term as we would usually have in our unitary case, plus the term which corresponds to the coupling of the to the event of coupling to the baths. So which happens with probability pk. And k can take two values, as in c and h, corresponding to the cold bath and a hot bath. And this will be phi k of rho minus rho, where phi k for the cold bath is when the cold bath goes in, the cold qubit goes into its thermal state, and the hot qubit just we trace out essentially from the initial state, the state of the C, and that will be the state of our hot qubit. And for the hot, it will be that the hot qubit will go into the thermal state, and for the state of the cold qubit, we just write that we just trace out the hot qubit from the initial state. Okay. So this is our equation, which describes the process that I just kind of described in words. As in, again, there with some probability, PC for the cold bath and pH for the hot bath, the qubit is coupled to the bath and their state is thermal, but this probability is not necessarily 1 at each time step. Okay, so I will not go into the details, but so in the exercise, you will be given already a steady state, and you will need to show that it is indeed a steady state of this equation. And then, given that steady state, you will need to quantify the entanglement. So the idea of this exercise is, again, like, because like if the probability of coupling to the baths would always be 1, like the states would always be separate, and there will be no entanglement between the cold qubit and the hot qubit. However, because the coupling to the bath happens only with a particular probability, we still have a chance that some correlations between these two qubits are preserved. And initially, these correlations are, of course, generated by this interaction Hamiltonian. But now we want to see like how good are these correlations. Okay, and for this, you'll need to use concurrence. So concurrence is one of these measures which are used to quantify entanglement. And it is a funny one. So C of rho is the maximum of 0, and lambda 1 minus lambda 2 minus lambda 3 minus lambda 4, where lambda 1, lambda 2, lambda 3, and lambda 4 are the eigenvalues of the matrix R, which is defined in the following way: square root of rho, or rho tilde, square root of rho, with rho tilde is sigma y, rho conjugate, sigma y. So rho tilde is like, okay, if we apply the y operator to each qubit, but also these two qubits are kind of in conjugated state. Yeah, and so this is a funny measurement entanglement between two qubits. And you need to quantify it for the steady state that is already kind of given to you. Yeah, and also find the concrete values of this concurrence for concrete values of the temperatures of the hot bath and a cold bath. So this second exercise, as many previous exercises, is based on the actual research article, which, so I always, when possible, I always kind of add references to this papers. Also, I added reference to the paper where kind of the concurrence is explained at length and introduced as well. Okay, so this shouldn't be a problem. And yeah, if you have any questions, you can always like ask them now or write me later. Like, everything works. Okay, then I guess this is all that I wanted to say for today. So maybe just to recap, the first exercise is about the Lindblad evolution, which is the extension of the Schrödinger equation for open systems. When we know that the environment is there in the background, but we don't want to think about it. And the second exercise is us trying to model the thermalization process, keeping in mind that thermalization can happen only with some probability, and then thinking, oh, in that case, can I preserve any entanglement between my systems?